Who's better, fast or slow pitchers? Major League Baseball is fast. Steals, diving plays, doubles, you name it. Speed controls the game, which is why it is crazy that pitchers who throw slow control the game also. We set out to find if there's statistical evidence to support that pitchers who throw faster are actually better than pitchers who throw slow. We chose this topic because we are interested in sports and recently had this debate amongst ourselves. I believe that pitchers who throw faster have more of an advantage as they give hitters less reaction time and will make worse decisions on pitches to swing at. Jack believes that there is no correlation and it is accuracy that determines a pitcher's effectiveness.
To analyze our data, we use a two-sample t-test for difference in means. One sample will be pitchers with an average pitch velocity of 93.8 miles per hour or greater. The other sample will be pitchers with an average pitch velocity of less than 93.8 miles per hour. We choose the number of 93.8 miles per hour because it was the value at the 60th percentile of both of our samples combined.
First, we randomly selected an MLB team from the 2023 season by assigning a unique number to each team and using a random number generator. We then assigned a unique number to each of that team's games and used a random number generator to select the game. Next, we accessed that game's data from an online source. After taking 80 samples, we divided the data into two samples, fast pitchers and slow pitchers. We classified fast pitchers as having an average pitch velocity in the 60th percentile or higher, which turned out to be 93.8 miles per hour.
Now that we have shown how we collected our data and set our parameters, we can move into our hypotheses.
Our null hypothesis will be set at mu1 is equal to mu2, with our alternate set at mu2 is greater than mu1. We can check off hypotheses on phantoms and head on to our assumptions. It was random as we used a random sampling method with a random number generator to ensure that it was random. It was independent as 350 and 450 MLB games was less than 4,860 total games played that season. And it is approximately normal as both sample sizes are greater than 30. With that, we can move into our test name, which is two-sample t-test for mu1 minus mu2. From there, we can obtain our p-value. Our sample mean 1 is 5.21, which would be the mean earned run average of fast pitchers. And this has a standard deviation of 5.825, with the sample size being 35. Our sample mean 2 is 4.718, which would be the earned run average of slower pitchers. This has a standard deviation of 4.426, with the sample size being 45. Again, with the alternate being mu2 is greater than mu1. This is how we calculated the test statistic of 0.593.
The p-value we received from our test was 0.722, with the degrees of freedom at 61.767. We have our alpha set at 0.05. Since the p-value is greater than alpha, we failed to reject the null. There's not convincing evidence that mu1 is less than mu2. Our test showed that there was no convincing statistical evidence that faster pitchers have a lower ERA than slower pitchers. The biggest problem with our study is that innings pitched had no significance to our results. Every once in a while, a randomly selected piece of data would show numbers similar to this: 1 innings pitched and 0 earned runs allowed. Other times, the data may show 7 innings pitched and 0 earned runs allowed. This is a problem because a 7-inning pitcher did something much better than a 1-inning pitcher, but they're valued the same in our final data because the pitchers have the same ERA. A way to get around this is by changing the response variable to whether or not the pitcher pitched a quality start. A starting pitcher records a quality start when he pitches at least 6 innings and allows 3 earned runs or fewer. Another dilemma that occurred to us while sampling also involves innings pitched. If a starting pitcher has a very bad performance, for example, 2.1 innings and 6 earned runs allowed, their manager would probably take them out of the game early. If the pitcher is taken out early and they haven't thrown many pitches, their arm might not be very tired and they would have left the game with a high average pitch velocity. To make this problem clear, pitchers that typically have an average pitch velocity of around 92 miles per hour after 6 innings or so, and are taken out of the game early with a high ERA and high average pitch velocity would inflate the mean ERA of fast pitchers. We saw this in our sampling when a pitcher left the game with 0 innings, 0 outs recorded, and 2 earned runs, leaving them with an infinite ERA. We are forced to disregard this data point, and the only way to adjust the problem is by filtering the database by games where the starting pitcher pitched at least 4 to 5 innings. Here's the graph with all of our data points. You can see it has negative direction with multiple probable outliers. It is linear with weak strength. That has been our video presentation for today. Thank you for watching.